Hello. So, fair warning, this is not going to be the most exciting lecture. It's going to be mostly math. So now we are moving on from one-dimensional motion, and we want to start to be able to describe multi-dimensional motion, particularly two-dimensional motion. And we will actually see that if you can do it in 2D, you can do it in 20D. But we'll start simple and stick with 2D. So what I wanted to do today was give a little bit of a primer on calculus, because we're going to occasionally need results that assume that you know how to take a derivative or do an integral. So I'm going to show you a couple examples of that. And I will say here that if you look on Moodle, there is a calculus crib sheet, which you are welcome to always have available on any quiz, any exam, whatnot. It will give you a list of some of the more common integrals and derivatives that we may have to take in this class. And they will not go beyond things like polynomials, sine and cosine, and maybe an exponential. So that crib sheet on Moodle essentially gives you all the answers, and you are, of course, if you are still taking calculus, welcome to just consult it if you need it. The good news is that derivatives are easier than integrals, and we'll mostly be doing derivatives. We won't really see integrals that much in this course until probably like chapter 7 or so. But I will nonetheless run through some examples and make sure that we are still remembering kind of the conceptual ideas behind the calculus techniques. And then I want to start introducing the ideas of vectors, which we have already we've seen, but in one dimension, but now we want to build upon that definition and do it in 2 dimensions. Alrighty. So my calculus primer. So let's start with the derivative. So again, remember, derivative is a fancy word for slope. If I have some position graph as a function of time, which for a given coordinate system might look something like this, for example, I could ask about what is going on. If this is a position, I could ask what is going on with, say, the velocity at a given point. And in previous lectures, we talked about how that is the derivative of the function at that point, which you can find by calculating the average velocity over increasingly smaller and smaller time intervals. That tangent line has some well-defined slope, which is, in this case, actually, in that case, it is just, we call it the instantaneous velocity. Which is the derivative of position with respect to time. We wrote it down looking like this, where I said the change in displacement or the change in time. As we look at tiny and tinier time intervals, that's what the limit as delta t goes to 0 means. We might write this as dx dt, and that is the definition of the instantaneous velocity. In a calculus course, you will see it written like this instead. So the idea is if I go up here, you have some function x of t that you want to calculate the derivative of at some point t naught, say. So what is the derivative at t naught, or t sub 0? You might see it written as x at t naught plus delta t minus x at t naught, all divided by delta t, and that is the velocity at t naught. So again, we're focusing in on some particular point in time, and we're essentially calculating the average velocity at that, using that point and some point just to the right of that point in time at t naught plus delta t. And as we let the delta t get smaller and smaller and smaller, we are finding the slope at that given location. So what you would do in a calculus class is you would actually use this formula that I've written in the bottom, and you would actually calculate rules of derivatives for functions like polynomials. So things that go like t squared plus 3t to the 5th minus t or something like that. Things that are just powers of t. The trig functions, the exponential, the logarithm, things like that. So I'm going to do a few examples to show how the answers come, and then I will give you kind of a general set of formulas. So suppose I have some position function, which is just 3 times t. Now we can visualize, remember in physics we can always think geometrically. Geometrically this is nothing more than just a line, a linear line, which itself has a constant slope. And if you remember kind of mx plus b, the equation for a line, we should expect that the slope in this case is equal to 3. Let's convince ourselves that is the case using the calculus formula. So I say to calculate the derivative, I have to plug in, I plug in t plus delta t, so it would first be 3 times t plus delta t. I subtract the function evaluated at t, so just 3 times t. Then I divide this entire mess by delta t. That is the same thing. I'll rewrite the limit. But now I'm just going to simplify, so I can multiply the 3 inside. There's the 3t that cancels with the other 3t. This ends up just being 3 delta t divided by delta t. It ends up just being the limit as delta t gets really small of the number 3. But it's just the number 3, so as I change delta t and make it bigger or smaller, that doesn't change the answer, so this is just equal to 3. So in this case, yes, it indeed appears that the derivative, as defined by the limit here, is just 3, as expected. What about something like this? So a polynomial that is now t squared. So this is a curve that is a parabola. As you get to larger and larger t, the slope appears to get steeper and steeper and steeper. So we should see that as t gets bigger, the slope should also get bigger. So let's actually then evaluate the slope. So first thing, I would say 3t squared, but I would plug in t plus delta t, all squared, minus 3t squared, all divided by delta t. Recopy the limit. So then I can multiply that out. So that becomes 3t squared plus 6t delta t plus 3 delta t squared, all minus 3t squared, all divided by delta t. That is then equal to the limit. Now just simplifying the 3t squared, then there's a minus 3t squared. So I see 6t times delta t plus 3 delta t squared, all over delta t. We can simplify this once more, because there's a delta t on the top and the bottom. So this becomes 6t plus 3 delta t. So now this is asking, as I let delta t get smaller and smaller and smaller, what happens to this function? I'm changing delta t only, and t is not changing at all. So essentially, where's my highlighter? So this term, since it does not depend on delta t, as I make delta t smaller, nothing happens. But this term, since it depends on delta t, as delta t gets small, 3 times delta t gets smaller and smaller and smaller, eventually just becomes 0. Then the answer just becomes 6 times t. So I would say in this case then the velocity, the function for velocity is equal to 6 times t for that position. And indeed, we do see in this case that as t gets bigger, the slope gets bigger. So remember, velocity corresponds to the slope of the position curve. So as you get to larger and larger times, the slope gets steeper and steeper. Now the way you would do this in a calculus class is you would derive general formulas that work for these things. So I'm going to just make a little table, and again, this is in your in that handout I referenced on Moodle. So in this case, the conventions is going to be a is just a constant, so just a number, and then n is also a constant, which is just a number. So one example could be that the function position as a function of time is just a constant. The position equals 3 meters for all time. physically I can think that seems like an object that's not moving. So I would expect in that case the slope is 0. And indeed, even if you go through the messier mathematical way, you calculate that the slope is 0. Probably not too surprising. Now what if I have some polynomial term? So I have some number times t to some power. So 3 times t squared we saw above, 3 times t. Negative 6 times t to the 4th power, or any of these sorts of examples. What happens is the overall constant just goes along for the ride, so a still follows through, but what happens to the derivative of the t to the n power, where again n is just a number like 2 or 3 or negative 6, is that the n drops down, and then you get t not to the n but to the n minus 1 power. So notice we saw that above. 3t squared, essentially the 2 dropped down, so it became 3 times 2, and then it became to the 1st power instead, which we wrote as 6 times t, which was the answer we derived. So the power goes down by 1. With derivatives, the power typically goes down by 1 every time you take the derivative. And the only exception is that this assumes that n is, I guess, not equal to 0. Though it still kind of works when n equals 0 too. Because when n equals 0, that's just a constant. Then the function is not a t to the n, it's just a, which we saw above. There is no slope, the derivative is 0. So that's the polynomial rule for derivatives. What about the sine function, which might have some overall constant? 2 times sine of t. Again, the constant goes along for the ride, and it just becomes cosine of t. The derivative of sine is cosine. Pretty easy. So does it go the other way? Is the derivative of cosine sine? Almost, not quite. It is minus a times sine of t. Sine becomes cosine, cosine becomes negative sine. You might think that's frustrating. Why is that the case? Well, again, remember, we can think physically. If I have the function of x, which is just cosine, that looks something like this, between 0 and 2 pi. Where it goes between positive a and negative a, whatever that constant a is. So I can ask, what is the derivative, which we know is just the slope of this curve, and I could pick a couple points and just do it on my own. If I look at the very beginning, I notice that the curve appears flat, so the slope appears to be 0, so I put down that the value is 0 there. Similarly, at pi and at 2 pi, the slope appears to be 0, so I know there are some points that are just 0. But then if I go to some intermediate point here, the slope is non-zero but negative because it's pointing downward. So the slope at that point might be something like this. Then when it crosses the axis, that's when it appears to be the steepest. So it's reached some minimum value in the velocity. And then it starts to flatten back out again as it goes towards pi. So then it rises back up and gets to 0. And then similarly on the other side, shallow positive slope, steep positive slope, and then shallow positive slope again. So it goes up and then comes back down. And indeed, if you look at this, it does look like sine, but it looks like it's flipped upside down. Hence the derivative is negative sine, not just sine. And then last, which may not ever come up in this course, is the exponential. Exponentials are great because they are their own derivatives. The derivative of an exponential is just the exponential back, which is pretty swell. Makes things simple. The only other thing we need to really know right here is that suppose I have multiple functions. which just could just be multiple terms, and I'll do an example of this right after this. The only thing we need to remember is that the derivative distributes across terms. So if you have a bunch of different terms and you want the derivative, you can take the derivative of each term individually. For example, suppose I tell you that my position as a function of time is 3t squared minus t plus 1. Then the velocity as a function of time is the derivative of this position curve. But by the distribution rule, what this is saying is it just takes, I can take the derivative of 3t squared, I can add that to the derivative of minus t, and then I can add to that the derivative of 1. The derivative distributes. Each of these individually are polynomials, so we can use the polynomial rule. 3t squared, we saw the 2 drops down, so this becomes 6, and then the power reduces by 1. For negative t, it's still a polynomial. It's t to the first power, so the 1 drops down, that does nothing, and then it becomes t to the 0, so that goes away, so it just becomes minus 1. And then the derivative of 1, that's just a constant. The derivative of a constant we said is 0. So then 6t minus 1 is our answer. If instead I say my velocity as a function of time is 6 sine of t plus t cubed, say, then I could say my acceleration as a function of time, which is the derivative of velocity, is the derivative of each of these terms, and then I add it together. Using my chart, the derivative of sine is cosine, so this becomes 6 cosine of t. And then the derivative of t squared is a polynomial. The 3 drops down, and then the power becomes a 2, so this becomes 3t squared. And that is the derivative. So on the homework, I have you do a couple of these, which is essentially like what I just did, where there's a function that's given to you that might be position, might be velocity, then it asks for either the velocity or the acceleration, which you get just by taking a derivative. And if you wanted to evaluate the derivative at a point, suppose I give you that the function is 3t squared minus t plus 1, and I ask what is the velocity at t equals 3 seconds. The first thing you do is what we did up here, where you first find the derivative, and then you just plug in the time you're interested in. So at 3 seconds, 6t minus 1 would become 6 times 3 minus 1, or 18 minus 1, or 17. So find the derivative, then plug in a number. The integral, which before we said all the integral is the area underneath a curve, which you can calculate by breaking the curve into a bunch of really, really tiny thin rectangles and adding up all the rectangles. So for example, if this were, say, my velocity as a function of time, and I do something that looks like that, the way to calculate, and I wanted to know, okay, given this velocity, how can I say something about the displacement? The idea was that I could take this curve and break it into a bunch of really tiny rectangles, each with a very tiny, small little delta t, and each of them with a height that is v evaluated at whatever it is at that point in time in that very tiny interval. Where the idea is that you make the rectangle so thin that v is essentially a constant everywhere inside that rectangle. And we saw that a couple lectures ago. I'm not going to draw all these rectangles, and then you just add them up. So the idea was we could write the total displacement was essentially the sum of all these rectangles that has some height v of t, the height of each rectangle, times the width of each rectangle. And the idea of making delta t smaller and smaller and smaller is you're making each rectangle thinner and thinner, but then you're getting more and more and more of these rectangles to add up. And then in that limit, it becomes the integral of velocity. The integral might look kind of crazy and abstract at first, but really, like, I like to think of it as kind of, if I think of like sine of t, you would never just write sine of t, or you would never just write sine. The trig functions only make sense if it's sine of something, in this case the sine of t, as I've drawn up top. I like to think of the integral as kind of the same way. You never just have the integral. You can kind of think of, the parentheses are kind of, this is the left parenthesis, this is the right parenthesis. It's the integral of whatever is inside there. So by, what we have written right here, we're saying it's the integral of what's inside, which is v, the velocity. Now, the fundamental connection that you make in a Calc 1 course is that integrals are nothing more than antiderivatives. If you can take a derivative, you could also undo the derivative, and that's the integral. We thought of the integral initially geometrically, but kind of the big fundamental, it's actually called the fundamental theorem of calculus. The big thing you do in a Calc 1 course is you show that the derivative and the integral are actually connected to one another. Going one way is the derivative, going the other way is the integral. We kind of saw that geometrically, but it is actually mathematically rigorous that they are what we call inverses of each other. So the fundamental theorem of calculus essentially says, and let me write it down and I'll explain it. If I have some function of t, the integral of some function between some point t1 and t2. So all I'm saying here is you're starting at t1 and you're ending at t2. So going back to our plot, like I could have called this t1, then it looks like I stopped here. I could have called this t2. It's the span of times I'm finding the area underneath. In this case, it looks like t1 is 0 and t2 might be 6 seconds or something. So I could write that the integral, I could possibly write that the integral from 0 to 6 of v dt or something, for example. But the fundamental theorem of calculus is saying that the integral of some function between some expanse of time is the same thing as the antiderivative evaluated at the endpoint minus the antiderivative evaluated at the starting point, where capital F is the antiderivative of f. I give you a function, you calculate the antiderivative, then you plug in the endpoint, and then you plug in the starting point, and you subtract the two answers, and that is the connection between derivatives and the integral. And this gives you a clean mathematical way of how to actually evaluate the integral. But I always like to start with an example where I can figure out the answer through two different avenues. So let's do the case where the velocity as a function of time is just, I don't know, let's say this is 3t. And I want to go between 0 and 2 seconds, which means v goes between 0 and 6 meters per second. I'm admittedly being sloppy and not putting units down, but sorry. So we've talked about in class how the way we could do this geometrically is we could just find the area under the curve. Delta x in this case what we would say is that delta x is the integral between 0 and 2 of v of t over time. One way to do it is think of it geometrically and just calculate the area underneath, which if you look at this looks very much like a triangle that has some height 6, some base length of 2. So I would say the area in this case is 1/2 the base times the height, or in this case I would get something like 6 meters if we're using SI units. Now let's actually use the more complicated looking thing you'll learn in calculus to make sure we get the same answer. So now we're going to do the same thing again. I'm going to evaluate the velocity between 0 and 2 dt. So what the fundamental theorem of calculus says is I should evaluate the antiderivative of v, I'll call it big capital V, plug in 2, then evaluate the big antiderivative and plug in 0 and subtract the 2. If I can do that, then we're off. Now again, v I called the antiderivative, but another way of saying that is to be an antiderivative, right? I could say if v is the antiderivative of little v, that is the same thing as saying the derivative of big V as a function of t equals v. Big V is the antiderivative of the little v, is the same thing as saying the derivative of that big guy just gets you back the original function little v. So what this amounts to is we have to think of what is the function where if I took the derivative of that function, I would get little v, 3 times t. What function, when I take its derivative, will give me 3t? In this case, it is 3 over 2t squared. And it turns out actually there's an overall constant. I'll just write this plus c, where this is a constant. And I think you can convince yourself if you go back to the first part of the lecture and look at the rules of derivatives, that if I took the derivative of that big thing, the 2 would drop down from the t, so it'd be 3/2 times 2. The 2's would cancel. The constant, the derivative of a constant is just 0. In this case, I would get back little v equals 3t. And this c is sometimes called the constant of integration, which ultimately will never really matter for us in these cases because it will always cancel out. I might even just stop writing it entirely. So then I would say the displacement from 0 to 2 of v dt is the antiderivative evaluated at 2. So I would say it's 3/2 times 2 squared. And I'll keep the c just to show you that it cancels out. Minus the antiderivative evaluated at 0. So 3/2 0 squared plus c. Notice you have a plus c here and you have a minus c here. So the c's and do indeed cancel out. This is just 0. So then it looks like at the end of the day I get 3/2 times 4, or 3 times 2, which is indeed 6. So you end up getting the same answer. But again, for this class, really, it's the fundamental ideas are the geometric ideas of how these objects relate to or how these quantities relate to each other. And we won't really need integrals until later in the course. But let me just write down a couple just to make sure you have a sense for what these might look like. So I will make 2 columns where I will write down the function, and then I will write down its antiderivative. So if the function is just some constant, 3, -6, the antiderivative is a times t plus a constant, which, again, we will never need. And again, you can convince yourself because you can take the derivative of what's on the right and you get back what's on the left. For a general polynomial, instead of the power going down, now the power goes up, and you divide by the new power. So similar-ish to how the derivative worked, but now instead of the power going down, the power is going up, and it ends up in the denominator rather than the numerator. The trig functions, again, we saw they kind of have a simple relationship. So you can just look at those in reverse. You should be able to convince yourself that this is true. The antiderivative of cosine is sine, because the derivative of sine is cosine. And then the good old exponential always is very well behaved. It's its own derivative, it's its own integral. Let me do one more example. Suppose I tell you my acceleration is, let's say 5 sine of t. And I want to know what is the change in velocity between t equals 0 seconds and t equals pi over 2 seconds. Well, I know that by definitions, by physics definitions, that the change in velocity is then the integral between 0 and pi over 2 of 5 sine of t dt. Where this thing I've written here, that is just a. But that is just the antiderivative evaluated at pi over 2 minus the antiderivative evaluated at 0. So if I figure out the antiderivative, I'm done, besides just plugging in numbers. The antiderivative, looking at our table here, sine becomes negative cosine, so then this becomes negative 5 cosine of t. Which again, you convince yourself if you take the derivative of capital A, you get back little a. And then plus a constant, but it will cancel out anyway. So then this becomes minus 5 cosine of pi over 2 minus, I'll put brackets so we can keep track of our negative signs, minus bracket negative 5 cosine of 0. Because you gotta be careful because you have the, it's endpoint minus starting point, but the starting point itself has its own minus sign. Cosine of pi over 2 is 0, so that goes away. You have the minus sign, so this becomes plus 5 cosine of 0. Cosine of 0 is just 1. The answer then just becomes 5 meters per second, for example. So the amount that the velocity changes between these two time points, in this case, will be equal to 5 meters per second between the start point and the end point. All right. Again, we'll see more derivatives and integrals in this class, so the first table is the one worth kind of getting a little bit more comfort with. Also, the good news is that you will see that sooner rather than later in your calculus class too. Alrighty, vectors. Vectors are incredibly useful tools in physics, so much so that essentially a quick Google search will reveal that there's a lot of resources out there to help you learn vectors. And we will actually use some of the online simulations that I like that help us more easily kind of plot and visualize vectors. So the kind of in-class session on vectors, we'll be doing some stuff on our laptops. to kind of help us visualize vectors. What I'm about to do makes more sense in terms of your learning if you kind of do it with me. So it's just going to be a lot of individual examples, particularly near the end. So really, I really would encourage you to, as I say things, to try to stop, pause, think about it a little bit, or go read your book first and then listen to this lecture and see if the book and what I'm talking about makes sense. So we're going to do everything up to kind of specifying vectors in a coordinate system. So first, we're going to do all this today first without a coordinate system. So I'm not going to worry about axes or anything, just going to talk about vectors as they exist as vectors. Now you've seen vectors in this class already. I've been using this word when we talked about 1D motion, and I said that displacement was a vector, velocity was a vector, acceleration is a vector. And I meant that in the means for one-dimensional motion, all that meant is that there was directionality associated with it. And in that case, we saw is that when the, say, velocity was positive, that meant the object was moving in the positive direction of your coordinate system. And when the velocity was negative, that meant it was moving in the negative direction of your coordinate system. That is actually part of a more general idea. So vectors, if I wanted to put down a definition for vector, I would say vector is a quantity with a magnitude. I'll put in parentheses, that just means with a length, with a size, and a direction. So again, it is quantities that have both some sort of magnitude, 30 miles per hour, but it also has a direction associated with it, 30 miles per hour to the east, for example. The convention is that magnitudes are always positive. And the directionality is what actually tells you whether you're moving in the positive or negative direction, for example. But the magnitude is always considered a positive number. And this is in contrast to something that we call a scalar, which is a quantity without direction. So something that might not necessarily have any directionality associated with it. So some examples of vector quantities that we'll see in this class. We've already seen displacement, velocity, acceleration, force will be a vector, momentum will be a vector, angular momentum will be a vector. There is directionality associated with those. You can't just say that there's a force acting on you. It's not meaningful until you say that there's a force acting on you in a particular direction. I experience very different realities if I have a boulder on top of my head pushing me down versus a rolling boulder that hits me to the side and pushes me to the right, for example. Both seem unpleasant, but they're nonetheless different quantities. Versus something like scalars that we'll see in this class. So like speed, for example, is a scalar. You can be moving at 30 miles per hour. That is your speed, but it's not telling you anything about the direction you're moving. Your mass is a scalar. Temperature is a scalar. We will learn that this quantity called energy is a scalar. Again, what I mean by like mass being a scalar is that there's no, I can't say, I don't know what the direction of mass means in this context. I have a given amount of mass and that's the answer. There's no, I have a given amount of mass to the east. And that's in contrast to say like all this quarantine life has caused my mass to increase. That's saying something different because that's saying how your mass is changing with time. Where with vector quantities, we're talking more about how things are moving and navigating through space. So, vectors are drawn quite simply. They're just arrows. So this would be an example of a vector. This is an example of another vector that's pointing in a different direction. This is an example of another vector. It's pointing in another direction, but has a much larger magnitude or length. So if I were to put down a ruler and measure the length of this vector, let's see, length of arrow equals the magnitude. And then which way the arrowhead is pointing is telling you something about the direction. To add a little bit of a third dimension, because we will see this eventually, this is typically the symbol that is used to mean out of the page. I think the idea is if you imagine like an arrow tip, if I'm looking straight down on the arrow tip, I see the point of the tip and then kind of the circle of the arrowhead. I don't know. And then if you see it with an X, that means into the page. Or into the screen, or into your piece of paper, or whatever it is. So you can have arrows that reside kind of in the plane of the paper. You can also have arrows that might point in and out of the paper. When you start to think in 3 dimensions, you have to include both, up and down, left and right, and then towards and away. All right, so vectors are nothing more than just arrows. And without a coordinate system, what I'm drawing here, I could draw this as an arrow, and that might be some representation of a vector quantity. Maybe that's my displacement, maybe that's my acceleration. It's telling me something about how much, let's say with displacement, it's easier to imagine. That arrow is telling me something about how much displacement has occurred and in what direction. That arrow, this arrow, this arrow, this arrow, this arrow are all the same length and all pointing in the same direction. We would say all these arrows, or all of these vectors, are equivalent. The vector itself, all it says, it has to tell you a magnitude, how much displacement or velocity or whatever it's representing, and in what direction it's pointing. There's nothing really special about where it's drawn to represent these two quantities. You just have to tell me magnitude and direction, and whether I draw it on the left side of the margin of the paper or over on somewhere else on the paper does not matter. All those 5 arrows I just drew are representing the same exact thing. Another way of saying this is that it's representing the overall effect, not the specific motion itself. It's not saying that, say, I started, right here and ended right here, for example. In order to do that, I have to actually lay down a coordinate system, and then it gets a little bit more complicated. Let me give a little notation. I will try to follow your book, but I'll also introduce kind of other notations that are out there so that you are not confused if you come across them. Suppose I have 2 points A and B, and I want to draw a vector that starts at A and goes to B. I might define this vector as AB with a little arrow sign over it. Vectors typically, I like the notation of your book, and it's what I prefer, that vectors will be written, a vector quantity will be written with a little arrow above it to signify that what I'm writing down is a vector, not a scalar. The other convention is to use boldface type for vectors, but it's less obvious to me. Like if I see the little arrow, it's clearly it's a vector. So again, just to pick apart the notation, you have your starting point, you have your end point, and then you have an arrow to signify that it is a vector. I'll even highlight that. So the quantity with the arrow, that is signifying the vector itself. If I want to talk about the magnitude of the vector, or the length of the vector, you will see usually the notation that I like is I like to put what kind of looks like an absolute value sign around it. So the absolute value sign is saying the length of whatever's inside, so the length of the vector AB. Or you might just see AB written without the little arrow. So if AB vector, if there's a vector AB, which I would write as AB with an arrow above it, if then later on you just see AB without the arrow, that could signify the magnitude or the length of the vector. Again, I'm less a fan of that because it's not obvious to me what that represents. Where if I see that AB is a vector and then I put little absolute value signs around it, that's meaningful to me. That says, okay, yes, I'm taking the magnitude of this vector. I'm asking what is the length of this vector that has the symbol AB. So that is what I will try to use. There could be some quantity, some point here C, and maybe I have another vector that starts at A and goes to C. I could write this as AC if that made sense. But again, the vector symbol is kind of like in algebra, how you can use whatever symbols make the most sense. You might see, for example, like if this were to represent a velocity, maybe you would write that as just V with a little arrow sign. And that's representing your velocity, which in the context, maybe it's obvious that it's between A and C. Or maybe you write V with a little subscript that's AC or something like that. As long as it's clear from the context what's going on, that's really what matters. Otherwise, it's just symbols. To keep things a little easier to kind of envision, let's stick with displacement. So suppose I have 2 points, A and B. And I start at A, I take some crazy path, there's even a loop, and I end up at B. We've talked about when we did one-dimensional motion that the displacement is just defined as the end point minus the beginning point. It's just saying where did you start and where did you end. Similarly, a displacement vector might be drawn something like this, where it's just an arrow that connects where you started, A, to where you ended up, B. Which again does not necessarily capture everything that happened in between, especially if there's a long expanse of time, for example, between point A, starting off at point A and arriving at point B. So I might say that AB vector is the displacement between points A and B. But isn't necessarily saying anything about what the actual path is, which I drew in red. Now suppose I hang out at B for a while, then I leave B and start my journey kind of going down here, And I end up at this point here, which we're going to call C. The displacement vector, I would say, starts at B, and ultimately I end at C. So this might be the vector BC with an arrow to represent the vector. Okay. So with these two, I could ask, what is my overall displacement? I started at A, I did this weird windy thing to get to, eventually to get to B, then I did another kind of windy path, I eventually got to C. Ultimately, I went from point A to point C. So maybe I'll do it in green. So ultimately, I started at A and I ended up at C. That is my overall displacement. A, C. So in this case, you can see I started at A, I did something and went to B, I eventually left B and went to C. That is the same thing as if I had started at A and just went directly to C. You know, in terms of the displacement vectors, they're conveying the same information. So this is what defines the addition law for vectors. That the vector AC, start at A, end at C, is the same thing in this case as start at A, go to B, and then start at B and go to C. So this is the vector sum rule. Again, the sum of all my intermediate steps is the same thing, gives me the same answer as if I would have just started at my starting point and went directly to my end point, which I think kind of intuitively makes sense. All right, I start at St. Mary's, I walk 3 miles east, and then I walk 3 miles north. You know, that's the same thing as if I went, you know, in a straight line. In that case, it would be 3 squared is 9, plus 2, 18. So that would be, by the Pythagorean theorem, kind of square root of 18, you know, distance to the northeast. Which would just be the straight line that connects me and my endpoint. Those vectors would represent the same displacement. Okay, so the idea here for vector addition, so there's a kind of a general rule for vector addition, is that you just place the tip of one vector at the endpoint of the other vector and add them up. Which, remember, it's a little bit more involved than just adding up numbers, because in this case now we are not just adding up numbers, but there's directionality associated with it as well. So in this case, I started at A, went to B. I could draw that as an arrow that pointed towards B. Then I left B and went to C. That motion was represented by a different arrow that I drew down here. And by drawing the arrows where the end point of one arrow is at the tip of the other arrow, I can get my overall displacement just by putting arrows, you know, endpoint back to back in a sense. So that leads to some questions. One you might ask is vector addition commutative? What is commutative? For just regular numbers, you know, if I have numbers alpha and beta, you know, 3 plus 5, alpha plus beta is the same thing as beta plus alpha. You know, for addition, you can, you know, it doesn't matter the order you add them up in, you get the same answer. That's the commutative property of numbers. So we could ask, since we're defining vector addition, we're using the same symbol, the same plus sign, does vector addition also obey this property of being commutative? So we can actually figure this out. So suppose I have some vector, I'll call it little a, and it points from one point to another. And then I have some other vector b that points in a different direction. This vector here would represent I first walked along A, and then I walked along B. So I might call this C equals A plus B. So now we want to ask, does the opposite order work? If I first walked in the direction of B and then walked in the direction of A, do I end up at the same point? So I'm going to do this just so that you are convinced I'm using the same vectors and not using some sort of magic to do this. I'm going to take the original and I'm going to color it a different color. I'm going to get rid of this. So that is the original path. We first did A and then we did B. Now we're going to do it in the opposite order. So I'm going to do it by highlighting B, making an exact copy of it, and putting it alongside, or putting it at my starting point. So this would be as if from my starting point, I first went along B, along the black line first. And then once I was done with that, walked along the direction of A. Copy, paste. And then you could see that, aha. Whether or not I first did A and then B, I got to the same endpoint as if I did first B and then A. And intuitively, perhaps this isn't too shocking. If I walk 3 miles east and then 2 miles north, I get to the same point if instead I had gone 2 miles north and then 2 miles and then 3 miles east. So in this case, we say that vector addition is commutative, like regular addition, which is good. Turns out vector addition is also associative, which just means that parentheses don't change the answer. The vector A, if I do something like this, that is the same thing as if I first did A plus B, and then added C. And that is the associative property. But this is the commutative property. That's more for the math majors. All right. So that's kind of nice because that means we can use kind of our intuition of how addition kind of works with regular numbers. It still also applies to vector addition. The ordering doesn't really matter when you're dealing with vector addition. In both these cases, going back to this drawing, in both cases, I ended up at the same place. The sum of the two vectors, whether I did A plus B or B plus A, got me to the same location. All right, so now I'm going to do, I think I have 6 examples of this sort of stuff. Let's see. I guess I'm going to be a little bit over an hour. Sorry for that. Just to kind of build up the properties of vectors. So, and you might do this too, and it doesn't have to be exactly the same vectors I use, but I'm going to draw a vector A that points straight up. I'm going to draw a vector B that points straight to the right. Then I'm going to draw a vector C that kind of points diagonally to the lower right. And then I'm going to ask, what is A plus B plus C? Now again, if I'm starting right here at this point, what this is telling me is I first walk in the direction of A. So I'll copy and paste that vector. So I first walk in the direction of A. Once I get to the endpoint of A, I walk in the direction of B. Again, putting the tip of one arrow at the endpoint of the other arrow. And then once I get to the location on B, I walk in the direction of C for some amount of length. And I end up right here. So again, a line that connects these two, I might call this D, which is equal to A plus B plus C. And I encourage you to then try to do the same exercise, but switch the order of A, B, and C. Like maybe first do B, then do A, then move in the direction of C. And you should always, no matter what the ordering is, always end up at the same point. Okay. Simple enough. What about B plus B? What can we say about that? So I'll make a copy of B. Suppose we start at some point and go out direction B. Then, just by the simple rules of vector addition, I go out another length equal to B and in the same direction as B. So I get ultimately over to this point. The sum of the two is some vector that points all the way from the start to the end point. I might call that D again, where D equals B plus B. And perhaps it's not too hard to see that if I were to ask, for example, what is the length of D? How long is that red vector I just drew? I hope it's clear that that is the same thing as twice the length of the vector B. It is twice as long because it's essentially just two B vectors side by side, or front to back. So the way with vectors that we write this is we can write B plus B, the vectors, is the same thing as 2 times the vector B. When you see a number times a vector, that's what's called scalar multiplication. (2b) is 2b, so this vector is just a vector that's pointing in the same direction as B, with twice the length. If the length of vector B was originally 3 meters, then the length of the vector 2b is then 6 meters long, for example. And scalar multiplication also obeys kind of the properties we would hope for. For example, if I have 2 times vector A plus vector B, mathematically what that's saying is I take everything in parentheses and add it to itself. So that's the same thing as A plus B vectors plus A plus B vectors. But by the rules of scalar multiplication that we just said, and the fact that the order doesn't matter, we can swap things around. I can write this as A plus B, which I can write as 2A plus 2B. So similarly, you have parentheses, you have a number outside, it can distribute in, or you could factor it out. Both work. Now, why do we call it scalar multiplication? Because notice I'm multiplying a scalar, a number that has no direction, with a vector that does have direction. That has specific meaning in this case. We will see later on in this course that there's ways that you can take two vectors and multiply them together. You have vector A times vector B. And that has different rules and different results. There's actually two ways you can multiply vectors together, and we'll see them both. the dot product and the cross product. And they're in chapter 3, so you can look at what they are now if you wanted to. But we're going to skip those sections and come back to those sections when we need them, which we won't need the dot product until we do energy. So that's after Newton's laws. And then the cross product will pop up when we do rotational motion. But scalar multiplication, a little bit more straightforward. So maybe this is not necessary to do. If I have a plus 2c, and I could ask what is this vector, at the end of the day. I could go back up to my vectors. Again, it's saying I start and I go some length a, and then I go some length equal to 2c, which is the same thing as if I went 1c, and then again another c. And so this is my starting point, this is my end point. The vector I might draw connecting them, that might be d equaling a plus 2c. If addition, then also subtraction. Does this have any meaning? We've just learned about scalar multiplication, so this I could think of as just the same thing as -1 times the original vector c. So all this does is if I have some vector c that might point like this, -c is just the same vector, -c is just the same vector. I'm going to get rid of, it's the same vector, but it points in the opposite direction. So -c is just the same vector, but it just is flipped and points in the opposite direction. So you could think, for example, if I were to say, okay, what is a minus c? What is one vector minus another vector? Let me call this 5. In that case, I can go back up to my vectors. I have a, which I will copy and paste. So I have a, but now I can think of this as, instead of a minus c, that's the same thing as a plus -c. So if I wanted to do the same rule where I put the end of one vector at the tip of the other vector, I could pull from what we just did, I can pull the vector -c, and I could add them together. So I could put something like this down, and then my final result, which I'll do in red again, starts here, points out here. It might be d. And I would call d in this case is equal to a minus c. The negative sign just flips the direction. The length is still the same. If it's 1 meter per second, it remains 1 meter per second, but just is pointing the other direction. And just so it's clear what this is, when we see it eventually, suppose I have a, and then I subtract a. You might think, if these were numbers, it would be 0. And indeed, if we just call this the 0 vector, or sometimes the null vector. And you can kind of see this if you look back up to what we did with c and -c. You can imagine I started at one point and I walked 5 miles to the east, then I turned around and I walked 5 miles to the west. Obviously, my overall displacement is 0. I'm back to exactly where I started. But if we're talking about directionality, we have to also think of it as a vector, so we call that the null vector. And it is the only vector where the magnitude of the null vector is 0. It is the only vector that has no length. All other vectors have some non-zero positive length and some direction that's associated with it. And so through these examples, and I'll zoom out a little bit so you can see these. Through these examples, you're seeing sometimes when we add and subtract vectors with one another, here I'll use 2 pens, is that sometimes they appear kind of, sometimes these two vectors, they're pointing in the same direction so that when I add them together, they kind of work together. My overall displacement is larger because they're kind of both pointing in the same direction. If they're pointing in opposite directions, my overall displacement is smaller because some of this guy is being canceled out by this one. Or if they're kind of at an angle from one another, in this case it goes up, but then it kind of backtracks a little bit, but also moves over to the side. So my overall displacement is something in between if they were to perfectly cancel each other out or perfectly add together. In the next lecture, when we think about the actual components, how to actually do this a little bit more with numbers, we will see this in more detail. But let me just write out a couple examples. And this actually, I think, is checkpoint 1 in your book, or it's very similar to checkpoint 1 in the book, where I'm going to take two simple examples here. Actually, I'm going to move over here. So I'm going to have some vector A that has some length 2, or if you can see on the paper as like two paper widths or lines. Then I'm going to have some vector C that has that has a length of 1 paper line. Now, those are my examples I'm going to copy and paste. So in this case, I'll look at 3 examples. So I'll copy A 3 times. I can look at the case where both A and C are pointing in the same direction. I can look in the case where they're pointing in opposite directions. And then maybe there's some intermediate case where I'll just do a perfect 90 degrees where maybe, I imagine some vector C that is pointing, perpendicular to A. And in all of these cases, I'm asking what is A plus C? What is the vector sum of these two vectors in the 3 ways I've drawn it? In this case, you can notice when they're working together, the vector sum goes all the way out and has a length, unsurprisingly, equal to 3. So if I say D is equal to A plus C for all of these, in this case, the length of the resulting vector is equal to 3. In the last case on the right, notice that the resulting vector starts at A, goes out 2 points, but then backtracks 1. So ultimately, the displacement just goes up 1. So in this case, I would say the magnitude of vector D is just equal to unity. Versus some intermediate where C is at an angle relative to A. So in that case, D goes straight up 2, but then also moves over to the right 1 unit, which is a different direction than A originally was moving in. And conveniently, if they're perpendicular to one another like that, you might notice that there's a nice right triangle there. One side of the triangle, I'll just copy it. One side of the triangle has length 2, the other side is length 1, and now we're asking what is the length of the other side, which is the hypotenuse, which is the length of vector D. So in that case, this is just square root of 5 by the Pythagorean theorem, which is about 2.2. So it has a magnitude or a length that's in between the two extremes of 1 and 3. So this will become increasingly important as we start to think about whether vectors are parallel to one another, anti-parallel to one another, or at some angle relative to one another. Those are all going to be very important cases we have to think about in terms of how motion evolves. One of these cases will be just purely speeding up. One of these cases will just be purely speeding down or slowing down. And one of these cases might correspond to, say, changing direction, which we will see once we get into circular motion and Newton's laws. All right, so that's the idea behind vectors in general. So next time we're going to think about how we can do vectors on a coordinate system where we can actually give some numbers down to pinpoint the actual locations of vectors. All right.